Hey chemistry class, today we're going to finish our notes for section 2B. So you'll need this page here with the temperature scales, that's page 13, and you'll also be continuing on and doing some practice problems on page 14 before you go on and do your homework for the day. So let's go ahead and dive in and talk about the two temperature scales that we use in chemistry and in science in general. The first one is the Celsius scale. Developed by Anders Celsius. You don't need to know his exact name or dates, but he wanted to come up with a new temperature scale based on two reference points. So he picked out two known temperatures that you could find. One is the freezing point of water, which you could find pretty reliably by getting some ice water. As long as it's a mixture of ice and water, it'll hold at a certain temperature, the freezing point. His other reference point was the boiling point of water, which again, you can get water to hold that temperature if you have it at a rolling boil. And he decided to take those two known temperatures, assign one a value of 0 and the other a value of 100. And that way you have these increments between the two reference points that are a degree Celsius. And so that's been a pretty standard scale used in science and in most of the world based on those 2 points. And it kind of makes sense to use water since that's such a common and important substance in our lives. But a guy named Lord Kelvin, a little bit later in the 1800s, he decided that wasn't a sufficient temperature scale to use for all chemistry problems. And it has to do with the definition that we came up with for chemistry that we defined yesterday. Temperature is the measure of the average kinetic energy of the particles. How fast are all the little atoms and molecules moving on average? So if temperature is actually a measure of speed or average speed, then a 0 on your temperature scale ought to correlate to 0 speed. That was his line of thought for the Kelvin scale. So he's going to come up with a scale where 0 is the lowest possible temperature you could have, and then you go up from there. So he also defined two reference points. One is something called the triple point of water. We're going to come back later in the year and talk more about that, but it's water under a certain pressure and temperature, and you can get boiling ice water basically at a very specific pressure and temperature. It's actually pretty close to the freezing point of water. His other reference point is that 0 mark that I said, where you would have 0 motion for the particles. We call that absolute 0. We're going to come back and write a fuller definition for that in a moment. And since he developed his scale based on this idea of molecular motion, where absolute 0 on his scale is 0 motion, all of the numbers that you get for the Kelvin temperatures are going to be positive. They can never be negative because while atoms can have a little bit of motion or a lot of motion or theoretically 0 motion, they can never have negative motion, so you would never have negative Kelvin temperatures. All right, so let's talk about that absolute 0 a little bit more, like I said. Okay. You need to know the values for absolute 0. I've got them in the value both in the Kelvin scale and the Celsius scale. It's 0 on the Kelvin scale, which is the lowest number the Kelvin scale has. If you convert that to Celsius, on the Celsius scale, it's negative 273.15. And we're going to use that number in our formulas coming up. So you can see it is very, very cold if you were to get down to absolute 0. And the thing about absolute 0 is it's actually a theoretical temperature. We've never gotten anything to be absolute 0 and have 0 motion, but it's the theoretical temperature where all of the motion would cease. So the molecules and atoms wouldn't be moving anymore. That's the definition for absolute 0. It would be the coldest temperature possible, but the thing is, it's actually not a possible temperature. We've got a third law of thermodynamics that you need to associate with the Kelvin scale and absolute 0. The third law of thermodynamics states that it is impossible to reach absolute 0. The third law of thermodynamics states that it is impossible to reach absolute 0. Let's think about why. How would you cool something down? What would you do to cool something down? You would put it in the refrigerator, you would put it in the freezer, you would put it in a colder environment, and that colder environment could take the thermal energy out of your object to lower its average kinetic energy, to lower its temperature. So to get something down to a certain temperature, you have to put it in an environment that is lower than that temperature so it can take out enough of the thermal energy. So if I wanted to get something all the way down to absolute zero, I would need to have an environment that's colder than absolute zero to take enough thermal energy away to get it to absolute zero. And that's not possible. It's not possible to have something with negative motion, which means it's not possible to have negative kelvins. It's not possible to be colder than absolute zero, which means I can't even get something down to absolute zero. We've gotten some objects very, very close to absolute zero, but we don't believe it's going to be possible to actually hit that mark. And that's stated in the third law of thermodynamics. All right, let's just look at some of the common temperatures so you can get a feel for what kind of Kelvin temperatures would be typical for like the temperature of the room that you're in, or things like that. Because we're most familiar with the Fahrenheit scale, which is sort of outdated, where, you know, if it's gonna be a high in the upper 80s today, maybe 90. That would be a pretty hot day for us. On the Celsius scale, that might look like upper 30s or mid 30s to be something in the upper 80s. On the Kelvin scale, a hot day like today might be in the 300s, the low 300s, which is a huge number, but that's because it's based off of zero being very, very, very cold. Boiling on the Fahrenheit scale is 212. On the Celsius scale, he defined it as 100. On the Kelvin scale, it's 373. So you'll see that a lot of our Kelvin temperatures, you can expect to get big numbers if you're dealing with everyday sorts of temperatures. The very coldest temperature we've ever recorded is negative 129 Fahrenheit. That's negative 89 Celsius. We're down in this range. We still have a pretty big looking number for Kelvin, which is 183. One nice thing about the Kelvin compared to the Celsius scales that I'll point out, the increments are the same. So notice if I start at 100 degrees Celsius and go down 10 degrees, the Kelvin scale has also gone down 10 Kelvin. So when you're converting between Celsius and Kelvin, it's just a really simple addition or subtraction problem. Fahrenheit, on the other hand, if the temperature goes down 10 degrees Fahrenheit, it does not go down 10 degrees Celsius. You can see the numbers don't match up like that. So it's a weird conversion for the Fahrenheit, but it is a conversion that we're going to do. So let's look at the math problems here. You need to know how to convert between any of these three temperature scales. We are going to include Fahrenheit since that's a common one for our country. I'm going to give you 4 formulas total. You really only need to memorize 2. One from each column. So you can either memorize this formula or this formula. You don't have to memorize both. You could just memorize one and rearrange it. So let's put all these up here and let you, I would suggest maybe just the first one in each column. If you know one from a math class, especially for Celsius to Fahrenheit, like it might have 9/5 or 5/9, depending on which direction the formula is written, that still works. 1.8 is the same as 9/5. And then here's the important key. We're using these letters, and they use them throughout this book, that you need to be familiar with. The capital T is a Kelvin temperature. So that's the variable you'll solve for if you're asked for Kelvin. It's where you'll plug in a Kelvin temperature if you're given Kelvin. We just use a plain old T for it instead of putting the little K with it because it's the official science unit for temperature. Then TC would be a Celsius temperature that you could either plug in that place or solve for that variable. And then the TF is a Fahrenheit. So why don't you get down at least the first one in each column, and then we'll practice using it. All right, so let's look at the practice problems at the bottom of the page. While performing an experiment, you collect a sample of gas in a bottle that's immersed in 32.50 degrees Celsius water. What is this temperature in Kelvin? So when you're looking at a problem, you need to look at what kind of unit you're given, the unit that goes with the number that you're given, and the unit that they're asking you for. In this case, they're asking me for Kelvin, and you need to choose the formula that has both of those units in it. So I need the formula that involves Celsius. All of them have Celsius in them though, and the one that also with the Celsius has Kelvin. So we could use the one that I had listed first in the left-hand column on the previous slide, because the capital T represents Kelvin, and then I've got my TC for Celsius. Then you'll plug in the number that you're given in the problem in place of the appropriate variable. So TC is representing Celsius. I can put my 32.5 in its place, and then I just add 273.15. Make sure you mark your answers with the proper unit. The unit here is Kelvin. That's what they asked me for. All right, on your second sample, we had temperature of seawater at the bottom of the Mid-Atlantic Ridge measured 671.50 Kelvin. What is the temperature in Celsius and what is it in Fahrenheit? Here's a little tip on this problem. I could have omitted the question about the Celsius and just asked you for Fahrenheit, and you still would have to do the same steps I'm going to show you, because you'll notice that no formula had the Kelvin, capital T, and the Fahrenheit in it at the same time. So if you're going from Kelvin to Fahrenheit or from Fahrenheit to Kelvin, you have to use both formulas. You have to go to Celsius first, and then from Celsius to wherever you're supposed to end up. So the problem setup it's asking us to do that, but we would have had to do it anyway, is my point. So for the first question, what's the temperature in degrees Celsius? I need to choose a formula that has Celsius in it and a Kelvin space, a capital T, because that's the number I have to plug in. So I've used the second formula that I had in the list, in the column on the left on that slide. I could have used the first formula though and just rearranged it and ended up with the same thing. Capital T is the variable for Kelvin, so that's where you can plug a Kelvin temperature in. And now we're subtracting 273.15, and I get 398.35 degrees Celsius. Then you're going to take that answer, that Celsius answer, and use it in a Fahrenheit formula. So now I've chosen a Fahrenheit formula that has a place for Fahrenheit and a place for Celsius. Plug in the Celsius that I just found, the 398.35, multiply it by 1.8, and then add. The order does matter. I've got it in parentheses here. Multiply first, then add. And you'll get 749.03 degrees Fahrenheit. So you can see this is very, very hot water. It would be boiling if it weren't under the very high pressure that it's under at that depth. It's still a liquid, but very, very hot. All right, so you're going to spend the rest of the class practicing using those formulas. First, I want to mention this page is about measuring temperature and energy. There's a couple units that we use to measure energy. These are on the Quizlet if you want to jot them down on this page. The joule is the science unit for work and energy, including heat energy. And then the calorie is an older unit measuring the same thing, energy, older unit for energy. So those will come out in different chapters throughout the year. All right, now you're going to practice using your Celsius and all the temperature conversions. And so on page 14, you just need to do as many of these problems as it takes for you to feel comfortable. I'm going to post an answer key so you can do a problem, check your answer, and then find, if you're getting it right, find a different sort of conversion. So try a Celsius to Fahrenheit. If you're getting that, then try Fahrenheit to Celsius. If you get one of those right, then go to Celsius to Kelvin. Do make sure you try one of these, either Fahrenheit to Kelvin or Kelvin to Fahrenheit, where you have to do the two steps, two different formulas. Once you've practiced these enough to feel comfortable, you've got two things to think about for tomorrow. There's a digital review for section 2B, which does include some of these temperature conversions. That's due tomorrow by class time. And then we have a quiz tomorrow over section 2B, and it will have a math problem on it, I believe. Hang on, let me check. Okay, I checked, and it doesn't have one of these particular math problems on it. Just to give you more time to get comfortable with it, it'll be on the test. There is a problem about which has the most thermal energy that we looked at in yesterday's lesson. All right, so those are your assignments for tonight. I will see you tomorrow with the last video lesson for the chapter.